Hello everyone, I am Nishant, a graduate student at the University of Wisconsin-Madison, and I am presenting our research on the design of multiphase motor windings for control of multiple air gap fields. In this presentation, I will first present the background for multiphase machines with multiple harmonics, and then present a generalized multiphase winding design technique that we have developed, which allows creating and independently controlling any number of air gap fields. We then present design examples to demonstrate the use of this technique in designing multiphase windings. The goals of this presentation are to present a technique which allows creating multiple air gap magnetic field spatial harmonics, that is, different pole pair fields, and control the magnitude and phase angle of each spatial harmonic using stator currents. So the harmonics that we are talking about are the spatial harmonic of the magnetic field in the air gap, which is created by injecting different stator currents in the stator windings. We will control the angle of the spatial harmonic and the magnitude. The spatial harmonics created in the air gap can be rotational, have a different number of pole pairs, or they can also be oscillatory. Oscillatory fields are not considered in this presentation since they have a single phase characteristic and do not contribute to creation of useful torque or force. Controlling multiple air gap fields with different number of pole pairs have been reported in literature for torque enhancement in electric machines, for magnetically levitating the rotor and thereby realizing bearingless machines, and for wireless power transfer in wound field synchronous machines. This often requires multi-phase machines with greater than 3 phases. Existing winding design literature is application specific. So, for instance, some of the references cited here focus solely on torque enhancement and do not consider the criteria required for bearingless machines or for wireless power transfer and so on. The technique that we are developing in this presentation is application agnostic and enables winding design to control any given set of air gap fields, irrespective of the application, and this opens up new avenues where one may want to design a machine to enhance the torque and have magnetic levitation, so on and so forth. So the winding design technique that we have developed allows independently controlling multiple air gap magnetic field harmonic. The inputs to the winding design method are the set of desired harmonics, that is, what are the pole pair fields that we would want to create, the number of phases that we would like to have in our machine, and the number of stator slots. The output of our winding design method is a valid winding layout that satisfies all the symmetry conditions, and stator currents that need to be injected to create the desired harmonic fields. Our winding design method can be briefly stated as follows. First, we determine the number of phases M subject to these constraints, followed by the allowable number of slots subject to these constraints, and finally we assign coil sides to the phases. Each of these constraints has a detailed mathematical derivation and implications, all of which can be found in our ECCE 2022 paper. They are not discussed in this presentation due to a lack of time. Once we know the winding design and the winding layout, we then need to determine what stator currents need to be injected to control the specific pole pair fields. It should be noted that currents of a specific sequence S in an M-phase machine control specific pole pair fields. A generalized expression for sequence S current in an M-phase machine is written as follows. As an example, for a 6-phase machine, the different sequence currents are plotted here. Zero sequence current has no phase shift between adjacent phases, while the first sequence current has a 60-degree or a 2 pi over 6 radian phase shift between adjacent phases. The second sequence current has 2 times 2 pi over 6 or 2 pi over 3 or 120-degree phase shift between adjacent phases. So this appears similar to a three-phase system. And the third sequence components have a 180-degree phase shift between adjacent phases. The steps to determine the appropriate sequence currents can also be found in our ECCE 2022 paper, and they are not discussed in this presentation. The expression for the sequence S current in phase K of an M-phase machine, which was introduced in the previous slide, is rewritten here. Using this expression, an analysis has been presented in our paper which shows that sequence S current in an M-phase machine can create different pole pair fields that rotate in the counterclockwise direction, in the clockwise direction, and also create oscillatory fields when currents of sequence S, which is an integer multiple of m by 2 or half the number of phases, is injected in a machine. As an example, the relation between the different sequence currents and pole pair fields for an m equals 6 phase machine is shown here. It can be seen that sequence -3 and sequence +3 currents have counterclockwise and clockwise rotating fields with the same number of pole pairs, resulting in an oscillatory field. Same is the case with the zero sequence current, which also have the same number of pole pairs rotating clockwise and counterclockwise, leading to oscillatory fields. The sequence -1 and -2 currents have the same set of pole pair fields but in opposite directions, as shown here. It can be seen from these results that appropriate sequence currents must be injected to control a given pole pair field. Higher number of phases allow injecting more number of current sequences. So now we go into the design examples to determine the winding layout and the sequence currents to be injected for creating a specific set of pole pair fields. The first example is to design a double layer winding that can create and independently control 1 and 3 pole pair fields. For this, by applying the winding design rules, we can find that a 5-phase machine with 10 slots and a coil pitch of 5 can be used. First, we draw the star of slots for H equals 1 or 1 pole pair field, and then for the 3 pole pair field. It can be seen that for this winding, it turns out that the winding factor is 1 for both the pole pair fields. We then arrive at the winding layout for the machine. Now that we know the winding layout, we determine the sequence currents to be injected. This current component I1 with an amplitude I1 hat and angle phi1 control the amplitude and phase angle of the air gap field of one pole pair, while the current component I3 with the amplitude I3 hat and angle phi3 controls the amplitude and spatial angle of the 3 pole pair field. FEA simulations are run first with just the I1 component and next with the I3 component, and it can be seen that indeed these create a 1 pole pair field and a 3 pole pair field. This is also run at different angles phi1 and phi3, and you can see the phase shift of the air gap magnetic field components. A simulation is then run with phi1 equals 0 degrees and phi3 equals 150 degrees with both I1 and I3 components, and this is how the air gap magnetic field with both the 1 pole pair and 3 pole pair field looks like. The second design example aims to create a double layer winding that can create and independently control air gap magnetic fields with 2, 3, and 5 pole pairs. For this, we require a 9-phase machine with 18 slots and a coil pitch of 2. The star of slots for H equals 2 or the 2 pole pair field, the 3 pole pair field, and the 5 pole pair field is drawn as shown here. It can be seen that the winding factors in this case are not always the same, and H equals 3 or the 3 pole pair field has the highest winding factor and the 5 pole pair field has the lowest winding factor. The winding layout is shown here. The stator current to be injected is determined by applying the rules which can be found in our ECCE paper. And this current now has three components, one of which controls each pole pair field. So the component in blue controls the two pole pair field, the component in red, which is I3, controls the three pole pair field, and I5, the green component, controls the five pole pair field. When all these three components are injected together in the stator current, at phi2 equals 0 degrees, phi3 equals 0 degrees, and phi5 equals 0 degrees, the air gap magnetic field, which contains the two pole pair, three pole pair, and five pole pair components, is plotted here. So in conclusion, this paper presented a design technique to realize multi-harmonic multiphase windings, that is, multiphase windings that can create multiple air gap spatial harmonics. The results in this paper show that any set of desired air gap field harmonics can be created by a multiphase winding, but based on the number of air gap field harmonics to be created, this may require a higher number of phases and slots. Given the desired set of field harmonics, the design approach that we proposed in this paper informs the winding layout and the current to flow through the coils for creating those required pole pair fields. The design examples and FEA results that we presented validate the multiphase winding design. This developed theory can be used to realize multiphase, multi-harmonic machines across different application domains such as torque enhancement, magnetic levitation, and brushless exciters for wound field synchronous machines. I thank you for your attention and for listening to this presentation. I would welcome any questions that you may have.